In this video, we're going to introduce chapter 9, which is on linear momentum and collisions. So we're going to define a new quantity that is called the linear momentum, and this is going to help us to study collision problems. So the picture that you see here is an example of a collision problem. So you can see that before, so this is a pool table. So before you have the purple ball and the yellow ball at rest, and the white ball is moving with some velocity. So this is the moment when the collision takes place, and then we can see that after collision, the white ball and the purple ball are at rest, and the energy is transferred to the yellow ball. So we're going to derive some equations that can help us to analyze these kind of systems. So now we're going to talk a little bit about the linear momentum. So suppose I have two systems. So I have a mass m1 that is moving with some velocity v1, and I have a mass m2 that is moving with some velocity v2. Then we can say that so there is a force F21. So this is the force. So this is the force on ball number 1 produced by ball number 2, and F12 is the force on ball number 2 produced by ball number 1. So Newton's law tells me that these two forces are just equal and opposite. So what that means is that you can rewrite this equation by saying that if you have an isolated system with no external forces acting on the system, then the sum of all the forces must be equal to 0. But we know that force is equal to mass times acceleration, so it means that m1 times a1 plus m2 plus times a2 is equal to 0. So if we write that equation, we know that a1 is just dv1 by dt. So we can write this by, so if we simplify this equation here, we end up with this equation right here. So that allows us to introduce a quantity here that is called the p-value. So the p-value is called the linear momentum of a particle, and it's just given by the product of the mass times the velocity vector. So we can see that the p-value is the product of the mass times the velocity vector. So because this is a vector equation, we can write it in terms of the x, y, and z components. So we can say that px is equal to m times vx, py is equal to m times vy, and pz is equal to m times vz. Now, because we know that the sum of forces is equal to mass times acceleration, and we know that acceleration is the derivative of the velocity with respect to time, and so if we rearrange this equation here, assuming that the mass is constant, then we can say that the sum of the forces is just the derivative of the momentum with respect to time. So this lets us to derive an equation that tells me the relationship between the linear momentum and the force. So we can say that the sum of all the forces acting on the system is just the rate of change of the momentum of the system. All right, so this is quiz number 9.2. I'll let you guys take a look at this quiz just to try to see if you can apply some of the basic concepts about the momentum. All right, so now we're going to look a little bit more into how to set up a system of equations that we can solve in order to analyze a system. So we've already said that if I have two systems, m1 and m2, and if m1 and m2 are interacting in such a way that the sum of all the forces acting on the two masses is equal to 0, that this tells me that I can rewrite this equation as this. So because we know that force is just a derivative of the velocity with respect to time, so I can end up writing this equation by saying that the derivative of p1 plus p2 is equal to 0. And so what this means is that if the derivative of the sum of p1 plus p2 is equal to 0, it means that p total, which is equal to p1 plus p2, must be equal to a constant. So, so what this is saying is that the total momentum of a system is not going to change as long as there is no external forces acting on the system. So we can rewrite this equation as saying that P1 initial plus P2 initial is equal to P1 final plus P2 final. Now again, because this is a vector equation, we can take this equation and break it into components. So we can write this as three different equations, one in the x direction, one in the y direction, and one in the z direction. All right. So generally, we know that whenever you have two or more particles in an isolated system in a rack, then the total momentum of the system does not change. So what this means is that if there is no external forces acting on the system, then the total momentum before must be equal to the total momentum after. All right. So basically, we're going to be focusing on a system where, so we have an isolated system. So an isolated system means that there is no external forces that act on the system. And so whenever you have an isolated system, it means that the change in momentum is equal to zero. And so this is the basic equation that we're going to be using to solve problems. So now let's look at this example right here. So suppose that we have so this is example number 9.1, which is the air chair. So suppose we have a 60 kilogram air chair that stands at rest on a frictionless ice and fires a 0.030 kilogram arrow horizontally at 85 meters per second. With what velocity does the air chair move across the ice after firing the arrow? So in this equation, we assume that, so we're going to apply the principles of momentum here to calculate the final velocity. So before we do that, we can write down the quantities that is given. So M1 is the mass of this guy right here. M2 is the mass of the bullet. V2 final is the final velocity of the bullet. So we know that the change in momentum must be equal to zero. It means that P final minus P initial must be equal to zero. So P final is equal to P initial. So P initial at t equals to zero, the system is at rest, so nothing is moving. So when we solve this equation, I get my V1 final, which is negative M2 by M1, V2 final. So if you plug everything there, you get a velocity of negative 4.25 centimeters per second. So notice that this is a velocity that is pointing in the negative I direction, so it's pointing into the left. So this is called the recoil. It's called the recoil velocity. So for the system to conserve momentum, the air chair has to recoil to the left in order to conserve momentum. All right. So now what if we have a system where it's a non-isolated system? So if we have a non-isolated system, it means that there is some external forces acting on the system. And so in this type of situations right here, I can say that the sum of all the forces acting on the system is just a change in the momentum over the change in time. So in this case, the total momentum before is not going to be equal to the total momentum after. So the momentum is changing, and so there is some external forces that are acting on the system. So in this example now, we can say that the change in the momentum can be written as the sum of all the forces acting on the systems times the change in time. And so if we can rearrange this equation here, we can calculate this change in momentum. So this is just P final minus P initial is given by taking an integral of the force with respect to time, going from some T initial to some T final. So this would let us define a new quantity that is called the impulse. So the impulse I is a vector that is given by the integral as a function of force, the integral of the force with respect to time. So this is a basic example right here. So suppose that we have a process where So we start from some T initial to some T final here. Then if there is a force that is acting within a very short period of time here, so the force only acts between Ti and T in the final, then I can calculate so by calculating the area under this curve, I can write the area. So the average value of the force is given by 1 over delta T, the integral from some T initial to some T final of the force times dt. And again, if you just rearrange this equation, then we can say that my impulse is just given by this average force times delta T. So again, this is really like a very useful equation that we're going to be using to solve some problems, right? To solve some few problems. So again, we can say that the impulse is just given by the change in force times the change in time. All right. So the relationship between the impulse and the momentum is that the change in momentum is just equals to the impulse. So we notice that in this example here, so we're talking about a system that is not an isolated system. So this is a system where there is a net force acting on the system. So if there was no net force acting on the system, the change in the P value would just be equals to 0. But because there is external forces acting on the system, the change in the P value is just equals to the impulse. All right. So we can look at this example here. So if you look at this example here, so this is an example of an airbag problem. So we notice that so each time that this car collides, so the airbags are going to explode, and because so when the car collides, it's going to come to rest. We can say that the force acts over a very short period of time, and so we can use that to introduce our change in momentum, which is just the I value, and this can be expressed as the average force times the change in time. So I can use this equation to calculate the total force that is exerted on the system. So again, so if we have a non-isolated system, then it tells me that the impulse there is a change in momentum, and that change in momentum is just equals to the impulse. All right. So this is a very, very useful example that we can look at. So this is example number 9.3. And so in this example, we're going to talk about bumpers. So how good are the bumpers? Now let's suppose that we have a crash test in which a car of mass 1,500 kilograms collides with a wall as shown in the figure. The initial and the final velocities of the car are given by, so the initial velocity is negative 15.0 meters per second, and this is going to the left, so to the negative I direction. And my V final is 2.60 meters per second, and going in the positive I direction. So if the collision lasts for 0.150 seconds, find the impulse on the car during the collision and the average net force exerted on the car. So this is a very useful example here. So you have a car that is moving with some initial velocity, negative 15.0 meters per second. Then once it strikes this wall, it's going to change directions and moves in the opposite direction with some velocity of 2.6 meters per second. So if you want to calculate the impulse, it's just the change in the momentum. So is the final momentum minus the initial momentum. We can write this as m V final minus mv initial. So this is just the mass times the V final minus V initial. So if you substitute everything here, you get an impulse that is 2.64 times 10 to the 4 I kilogram meters per second. Then I can calculate my average force as impulse over change in time. That would give me a value of about 1.76 times 10 to the 5 I newtons. Now, what if the car did not rebound from the wall? So in this case, the car is going to come to rest. And so in that case, because the final momentum is 0, then if you substitute everything here, you calculate a new impulse, and we can use that to calculate the new average force, which is going to be smaller. It's a much more smaller net force. compared to the previous force when it doesn't come to rest.